Geometry students, in this lesson we are going to be talking about two different laws that you're going to use to draw conclusions from statements. So this is going to be a lot like what we've been talking about when we talked about conditional statements and we talked about inductive reasoning way back in lesson 7. Now though, we're going to be using a different type of reasoning other than inductive reasoning. Now let's just take a moment to review what inductive reasoning was. Inductive reasoning is reasoning from specific to general. I find a specific case of something happening, and then another specific case, and another specific case. And then it happens again and again and again, where if something occurs, then another thing occurs with it. And I make all of these individual observations. After making many, many observations, eventually I just come to the conclusion that if one thing happens, or if one thing is true, then another thing is true because I've never observed anything to the contrary. That's what our truth tables were based on. Our truth tables were based on inductive reasoning. And for inductive reasoning, we find a bunch of specific examples. And honestly, to prove from inductive reasoning, from that kind of reasoning, what we would have to do is look at every single possible example of a thing. And then once we've looked at every single possible example, and every single example has been true, then we know that the statement is absolutely true. Until we observe every single example, we're always on the lookout for a counterexample. And we know from our truth table, a counterexample occurs when our hypothesis is true, but our conclusion is false. So we're always on the lookout for a counterexample. For example, one of the conditional statements we used in the past was if an animal quacks, then it is a duck. So I'm always looking for animals that quack. And if every single time I see an animal that quacks, that's a duck, I'm going to conclude that that's a true statement. If an animal quacks, it's a duck. Until I run into a counterexample. I always have to be on the lookout for a counterexample, because until I've observed every single animal that quacks in the entire world, I can't actually say with absolute certainty that I've proven that conditional statement to be true. But once I find just one counterexample, so I can have a million examples and not prove my statement because I haven't observed every single example, but it just takes one counterexample to disprove. That's inductive reasoning. Now we're going to be working with another type of reasoning known as deductive reasoning. And we're going to learn two laws related to deductive reasoning in this lesson. For deductive reasoning, we use logic to draw conclusions from given facts, definitions, and properties. Wait, what are facts, definitions, and properties? They are things that are generally always true. So with inductive reasoning, we were reasoning from specific examples, specific, and then making a general conclusion. Okay, every single one of these animals I've seen that quacks is a duck. So I'm just going to say that all animals that quack are ducks. This is the opposite. With deductive reasoning, I'm taking facts, definitions, and properties, things that are always true for everything. We know that they're true. We've already proven them true. And then I'm reasoning that specific examples of those things are true. Deductive reasoning is much, much more rock solid than inductive reasoning. All right, let's take a look at an example of what deductive reasoning looks like. And we're going to be looking at a specific example of deductive reasoning here. So here's a general statement that I've deemed to be true. I've proven this true. The bakery makes fresh bread every morning. Okay? The bakery makes fresh bread every morning. It is morning. Now, can I draw a conclusion from those two statements? Why, I sure can. I can draw the conclusion. Therefore, the bakery is making fresh bread. This is deductive reasoning. I take a general statement that I know is true. At least I assume it to be true. And then I can look at the parts of the statement. Now, here's the thing about this. This statement is not like the other statements we've been working with. This is a statement you would encounter in the real world, but this is not a conditional statement. Hey, maybe it would be better if we change this statement into a conditional statement. The bakery makes fresh bread every morning. Okay? So I wonder if we could say, if it is morning, the bakery makes fresh bread. If it is morning, the bakery makes fresh bread. Is that an equivalent statement to what this says? Why, yes, it is. Conditional statements can be general statements of fact. If it is morning, the bakery makes fresh bread. Then I can say it is morning. Right now, it is morning. Therefore, the bakery is making fresh bread. All right, let's take a look at what we just did here. This is an example of what's known as the law of detachment for two statements, P, a hypothesis, and Q. When if P then Q is a true statement. So we did have to write it as a conditional statement. Just want to make that emphasized here. We have to make sure that we take casual statements like this and turn them into conditional statements so that we can analyze them properly. If the phrase, if P then Q is a true statement and P is true, then Q is true. Now here's what we're doing. We're basically detaching, the law of detachment, we're detaching the hypothesis and the conclusion from the conditional statement. And then we're drawing the assumption that if the statement is true, drawing the conclusion, I suppose, that if the statement is true, then if the hypothesis is true, then the conclusion is true. And that's what we're doing with the law of detachment. Let's take a look at another example of this. If it is Monday, then Mark will go to work. If it is Monday, then Mark will go to work. This is already a conditional statement. I don't have to do anything to this to change it to a conditional statement. Oh, today is Monday. What's my conclusion? Conclusions, by the way, always end with the word therefore. Okay, so law of detachment conclusions are going to begin with the word therefore. Therefore, Mark will go to work today. All right, that's the law of detachment, pretty basic. If we have an if P then Q statement, that's correct. If P is true, today is Monday, Q is also true. Therefore, my conclusion, therefore Mark will go to work today. That word therefore is very important for your conclusion from the law of detachment. All right, we have one more law, the law of syllogism. The law of syllogism relates three statements together. This is going to be a lot like the transitive property of congruence. So look at what this is. If P then Q, if P then Q is true, and then if Q then R is true, we've already deemed them true. This is deductive reasoning. So we've already established that these are true statements all the time. We're not looking for counterexamples. We know there are no counterexamples. But if I know if P then Q is true, and then if Q then R is true, I can state if P then R and skip the middleman. I can get rid of Q. Let's take a look at an example of the law of syllogism. If there is a power outage, then the freezer does not work. Oof. If the freezer does not work, then the ice cream will eventually melt. Now, we don't really need the word and here. It's here as sort of a convenience. Really, we just need if P then Q. Now notice this Q is the hypothesis, this conclusion is the hypothesis of my next statement. If the freezer does not work, so if Q, then R, the ice cream will eventually melt. Well, I can cut out the middleman and write a conclusion. If there is a power outage, then the ice cream will eventually melt. I can get rid of the Q statement because the Q statement was an eventuality that led to the R statement, okay? So if I have a statement whose conclusion is the hypothesis of a different statement, I can cut out that conclusion and hypothesis and just say if there's a power outage, then the ice cream will eventually melt. All right, let's take a look at some practice problems involving the laws of detachment and the law of syllogism as we use deductive reasoning to solve some problems.